Yeah, thank you for inviting me. And I'm going to talk about unification of gravity and inertia in classical non-relativistic physics, as we already heard something about by Jonathan yesterday, and a following Soliton model of elementary particles, which is suggested by such a unification of gravity and inertia. Yes, and I begin with the unsolved problems in classical physics. There exist many unsolved problems in classical physics, like Newtonian mechanics and electrodynamics. And examples of this are the origin of inertia, the 1/r singularities in the Coulomb law and gravitational law, and the infinite self-energies. And those problems are carried over to modern theories, which build on those classical theories. For example, the renormalization. And the plan is to take those unsolved problems as starting points to search for alternative theories. And because those may be the points where we took a wrong turn in history. And the solutions to those problems indeed turn out to have remarkable consequences and suggest a different approach to quantum relativistic theories. And we begin with the origin of inertia in classical non-relativistic physics. Yeah, what is the question of the origin of inertia about? Yes, the question, why do bodies tend to maintain their state of motion? And what causes the forces that bring this about? And the problem is present since Newton's days, and because the fictitious forces in Newtonian physics are postulates, as is the geodesic equation in general relativity, or the classical version is Newton's second law. And the question can basically be divided in two sub-questions. First is what causes the inertial forces when a body accelerates, and the second is relative to what does a body tend to maintain its state of motion. And for the first question, there was no answer given by Newton. It is just a postulate, the inertial forces. And one hint is the equivalence principle, that these forces might be of gravitational origin. It was first proposed by Friedlander, as Jonathan said yesterday already. And the second question was answered by Newton, and he said it is relative to a postulated absolute space, and he tried to prove this in his bucket experiment. Yeah, what is Newton's bucket experiment? He tried to prove the existence of absolute space with it, and it is a bucket filled with water, hung up by a cord and then twisted, and the bucket is held in place. And at this point, the water is flat. And then the bucket is released and it starts spinning. And at first, the water remains at rest because it is not immediately dragged with the bucket, and it remains flat at this point. And then after some time, the water is dragged around with the bucket, and it starts to curve up at the walls. And Newton concluded that it is not the rotation of the water relative to the bucket causes the inertial forces, but relative to absolute space, because in the moment when the water is not rotating relative to the bucket, it remains flat. And in the moment when the water is rotating relative to absolute space, it is curved upwards, even though it is not rotating relative to the bucket, it is co-rotating with it. Yeah, and this interpretation was later challenged by Mach, and he argued that the rotation of the water relative to the distant stars gives rise to the inertial forces, and that the apparent irrelevance of the water's rotation relative to the bucket is just because the bucket has negligible mass compared to the rest of the universe. And yes, this is what the sentence yesterday was also about, that no one could say how the experiment would turn out if the walls became ever thicker and thicker, ultimately comparable to the size of the universe. Then maybe this rotation of the bucket would play a role in whether the water is curved up or not. And there is observational evidence for Mach's hypothesis. And this is the measurement of the rotational velocity of the Earth, one time via observation of the distant stars and one time via Foucault pendulum. And one measures the rotation frequency compared to the distant stars, and the other would, according to Newton, measure the rotation frequency relative to absolute space. And both yield the same angular frequency for the Earth. And this is a coincidence in Newtonian mechanics, but it is predicted by Mach. So this can be counted as an observational evidence in favor of Mach's principle. And yes, Mach's principle states that bodies tend to maintain their state of motion relative to all other masses in the universe. And as a consequence of this, inertial mass is not an intrinsic property of bodies, but it is a result of an interaction with other masses. And it should vanish in empty space because of that.
Let me make sure I understand the Foucault pendulum and the state of the Foucault pendulum maintained its angular momentum around a certain axis, and that axis was, as far as we could tell, stationary with respect to the stars in the universe.
No, with respect to absolute space in Newtonian physics.
You were talking about an observational evidence first.
Yes.
So what were the two things that agreed again?
If you measure the rotational frequency of the Earth by observing the distant stars, then you get the rotation frequency relative to the distant stars.
Yep.
And with the Foucault pendulum, according to Newton, you get the rotation frequency of the Earth relative to absolute space. But according to Newton, they do not have to match. It is a coincidence that they match. But according to Mach, they should match, because the Foucault pendulum, according to Mach, would also measure the rotation relative to the distant stars, but not to absolute space.
Well, in the Newtonian scheme, it's not entirely a coincidence because if the distant stars are also moving inertially, you would not.
Yes, but if you would have to postulate that the distant stars do not rotate, then you would get it. Yes. Yeah. But this is an additional assumption that you have to put in.
So Mach, I just add that he proposed both kinds of hypotheses and was open to both there being an intervening medium that was responsible for both, or for the masses. So
okay.
This is the one he's trying to.
Okay. Yeah, now I come to the inertia-free mechanics. This was originally proposed by Hans-Jürgen Schroeder, and it is a way of implementing Mach's principle and the unification of gravity and inertia. And first we saw already that from the validity of Mach's principle requires that the Lagrange function of the universe is only dependent on relative quantities. And it was pointed out by Barbour that the Lagrange function has to be invariant under this transformation. A is an arbitrary rotation, it can be time dependent, and G is an arbitrary displacement vector. And the Newtonian kinetic energy obviously doesn't fulfill this requirement, and so we have to modify it and write it as a sum over all particles in the universe of the relative velocity squared and some function f, which accounts for possible distance dependence. And yeah, one can already see the similarity of this with the gravitational potential and the equivalence principle, so the observed equivalence between gravitational and inertial mass, suggests that we take this f of r here as proportional to 1 over r. And from dimensional reasons, you get this equation, this function. And if you put this in, you get this for the kinetic energy. Yeah. And this together with the Newtonian potential yields this Lagrange function. It is the Lagrange function of the inertia-free mechanics. And now the kinetic and the potential energy are represented by a single velocity-dependent gravitational potential. So we don't have a separate kinetic energy now. And it is invariant under all transformations of this form. About rotations I will talk in a second. And it is not just the Galilean transformations, which are only valid if v is constant, but it is for arbitrary position vectors. So they are valid in all linear accelerated frames. And as a consequence of this, the inertial force m times a appears automatically in linear accelerated frames, and they disappear exactly in that frame, which is unaccelerated relative to all other masses in the universe. And the inertial force is a real part of the gravitational force. And yes, now we come to the unification of gravity and inertia. we have no separate kinetic and potential energy, but only one single velocity-dependent gravitational potential. And the g in this equation here, in this one, in the Lagrange function, is just a multiplicative constant. So we can just omit it and leave it out, because the Lagrange function is invariant under any rescaling. And as a consequence of this, we do not need to postulate the gravitational constant. And this is not possible in Newtonian mechanics, because the kinetic energy is not part of gravity, and thus it is not proportional to g. And also, here we only have gravitational masses. There's no inertial mass present here. Those are gravitational masses because it is a gravitational potential. And so we do not have to postulate that either. And if we calculate the equations of motion from this one here via the Euler-Lagrange equations, we get in the lowest order V over C. We get this for the acceleration. We have this term on the right side here, m times a, equals, and this is the Newtonian gravitational force apart from the gravitational constant. And we can read off that this here is the inertial mass. So we get for the inertial mass, oh, this is a little bit shifted, the arrow should not be there. It is 2 times phi over c squared times the gravitational mass. And this is basically what the equivalence principle is saying, namely that the inertial mass is proportional to the gravitational mass. And the proportionality factor is this 2 times phi is this term here, over c squared. And it is a result of the gravitational interaction, obviously, because this is the gravitational potential. And it vanishes in empty space, because in empty space, this term here is 0, and we have no inertial mass. So it satisfies the requirements of Mach's principle. And yes, it is a scalar and not a tensor, and thus it is also isotropic. Because an anisotropy of inertial mass is ruled out by experiment, and this has long been a problem for Machian theories, especially those based on the Weber potential, like Schrödinger and Reisner that we saw yesterday. Yeah, and if we solve this equation here for the acceleration, we can compare the right side with Newton's law of gravity, and we get for the gravitational constant that it is just the inverse of the proportionality factor between inertial mass and gravitational mass, and it is c squared over 2 times phi. This expression takes place of the gravitational constant, and it agrees with observation. If you plug in the values of the universe in this formula, then you get the right value of g, and this is the flatness condition of relativity. Yes, and you can explain the strength of gravity with this. Where does the g come from? It is the inverse of this proportionality factor between the gravitational and the inertial mass. And yes, since we have such a huge amount of mass in the universe, we have a large induced inertial mass and thus a weak gravity. And if there were less matter in the universe, gravity would be much stronger. And yes, the full equations, just for completeness, the full equations resulting from this yields those ones here. It includes gravimelectromagnetism at the higher orders. And the inertial forces then come out of this inductive term there. This yields the inertial forces in accelerated frames, similar like the work of Sharma. Yeah, and we can also make the Lagrange function rotation invariant to satisfy this requirement by Barbour. And then it looks like this, and I will not go into the details. But then the theory will be valid in arbitrary accelerated frames, linear and rotation. And all inertial forces appear automatically in any frame. And they disappear exactly in that which is unaccelerated relative to all other masses in the universe. And the inertial forces are a real part of the gravitational force then. And yes, frame dragging is then really a consequence of Mach's principle. It arises in this purely classical framework. And the equations look very similar for the frame dragging than they do in relativity. But in this theory, you have a complete equivalence, whether the bucket is rotating or the universe is rotating. So if the bucket was stationary and the universe was rotating with omega, then you would get exactly the Newtonian centrifugal force just as if the bucket were rotating and the universe was stationary. So there is a complete relativity of acceleration, linear and rotational, present in this theory. Yes, conclusion for the first part. Inertia can be explained as of gravitational origin using this velocity-dependent potential. It is a fully implementing Mach's principle, complete relativity of acceleration. The theory is valid in arbitrary accelerated frames, and the inertial forces arise automatically as a part of the gravitational force. Inertial mass, inertial forces, the weak equivalence principle, that is the proportionality between inertial mass and gravitational mass, and the gravitational constant do not need to be postulated, but they can be derived from the theory. And yes, one can explain the gravitational constant from this. It is the inverse of the proportionality factor between inertial and gravitational mass, and from this results an explanation of the strength of gravity. And it also shows that in common theories, the inability to explain G is tied to the inability to explain inertia. This also comes out from these theories by Schrödinger and Assis, and that are based on the Weber potential. They also can derive a formula for G because they are also able to explain gravity as of inertia as of gravitational origin. But they have this problem with anisotropic inertial masses, and they are ruled out by experiment. Yeah, now we come to the second part, which is the soliton model of elementary particles. This is a plot of such a soliton, which is an internal oscillation in 2 dimensions, and works the same in 3 dimensions. And yes, we get to that now. Let's first talk about the consequences of such a unification of gravity and inertia. In common theories, inertial mass is an intrinsic a priori property of particles, and especially it exists independent of the presence of any fields or stuff like that. So particles just have an intrinsic property, which is inertial mass. And this situation has now changed. In the unification of gravity and inertia, we saw that inertial mass of a particle is proportional to this expression. So it is no longer an independent property of the particles, but a consequence of their gravitational mass and the gravitational field. And thus only gravitational mass remains as fundamental. But the gravitational mass only has a meaning in relation to the gravitational field. It has no meaning outside of it. And thus, the gravitational mass and gravitational field are on the same fundamental level. And the concept of gravitational mass has no meaning without the gravitational field, and vice versa. This suggests that gravitational mass is a special manifestation of the gravitational field, and that particles are some kind of localized lumps of field energy in the gravitational field. Or maybe some kind of unified field which contain both the gravitational and the electrical, given the similarities that those fields have. And yes, a natural candidate for such a lump is the soliton. What is a soliton? It is a... Yes, sure.
Okay, yeah, sorry.
Yeah, what is a soliton? It is a localized, self-enforcing, stable propagating wave packet which preserves its shape under collisions, and it owes its stability due to a balance between dispersion and nonlinearity. So it is an intrinsically nonlinear phenomenon, and only nonlinear partial differential equations have soliton solutions. And they behave like particles of equal masses when colliding, and they exhibit wave and particle properties, which naturally leads to the wave-particle duality when treating particles as solitons. And integrable equations exhibit analytic n-soliton solutions, and they describe n-solitons and their interaction and the resulting motion in a single solution. And this is very similar to the universe with n particles and their fields, and it can be used to describe the universe. Yes. As an example, we have the Korteweg-de Vries equation. It is a shallow water approximation of Navier-Stokes equations. And yeah, it describes surface water waves in shallow water. And we can see here that the second term here is the nonlinearity, and the third term is dispersion. And it has n soliton solutions. And the single soliton solution is given by this here. It's one of those lumps here. And the animation on the right side shows two solitons of this KdV equation colliding. And wait for it a bit. And you can see that the faster soliton hits the slower one. And then the slower one after that has the velocity of the faster one and vice versa. But the important difference here is that it is not two points colliding and exchanging the momentum at a discrete point in time, but it is continuously mediated via the fields of those solitons. So not the core regions, but you see that it is a continuous process. It is not discrete in time. Yeah, and this also nice, yeah?
You said there's an exchange in velocity, but I just see an overtaking. Everyone is maintaining its velocity. Or
That's what you think of.
The group velocity.
Well, you can think of this as
Yeah.
getting the other and the other coming off, or as one going through the other.
Yes, you can think of it both ways, yeah. Yeah, this also relates to the non-distinguishability of particles in quantum mechanics. And yes, it has a nice connection to de Broglie's double solution theory. De Broglie initially postulated that every particle possesses an internal oscillation. The left one is for a stationary particle, and the right one is for a moving one with a constant amplitude. And this was later developed by Schrödinger to his wave mechanics. And de Broglie always considered it as incomplete. And he said it is only the phase, and this constant amplitude is not the true amplitude, but that the complete description should be of this form, with this psi being the internal oscillation and the f being a variable amplitude. And this has a maximum at a particle's position, and it decays far away from it. And this u here should obey a nonlinear equation. Yeah. And this is exactly the structure that a specific type of soliton has, namely the breathers. And as an example, we consider the one-dimensional sine-Gordon equation. This is a nonlinear wave equation. The sign here is the nonlinearity. And it admits breather solutions of this form here. And this has exactly the form postulated by de Broglie. We can identify the cosine here as the internal oscillation part, and the f of x here is the amplitude part. The arctangent doesn't change anything. It is just a scaling function. It is a continuous function, and it doesn't change the overall structure. And this is not specific to the sine-Gordon breather, but it is common to all breather solitons of relativistic field equations, the structure here. Yeah. How can the gravitational field support soliton solutions? Yeah, let's consider the simplest relativistic field equation. It is a relativistic version of the Laplace equation in Newtonian mechanics. And then we apply our conclusion that the mass is a part of the gravitational field itself. So we plug in here some function of the field for the rho and the constants on the right side. And then we get a nonlinear equation that can sustain n soliton solutions, and indeed they have already been found. Equations like that have been studied, and they have found n soliton solutions for those equations. And especially interesting are equations which have this form here, where the potential on the right side depends only on the modulus of the field. Then you can always find solutions which have the form of de Broglie. You can write them as e to the I omega t times some amplitude factor. And a concrete example, which is analytically solvable, is if v of phi has this form here, then you get such a wave packet here. Yeah?
What are we physically talking about here? Is this a mathematical description of gravitational waves?
No, it is a we want to find soliton solutions to such an equation, or show that the gravitational field can indeed sustain soliton solutions.
So wouldn't that be gravitational waves?
Yeah,
What
well,
would
the
a
gravitation
soliton solution to a gravitational field, what would that physically be?
particles.
Of gravity?
No, just particles in the field. They would the energy which is contained in the soliton is then a particle. The gravitational waves are just linear, and the solitons are nonlinear.
So what physical existent are you describing here?
Particles.
What type?
Masses.
Like masses?
Yes.
Massive objects, okay.
Yes, massive objects. Yeah.
And they produce gravity themselves.
Yes. Yes, they are part of the gravitation field here. Yes, and such a lump here is then constitutes an extended particle, and it is localized in three-dimensional space and oscillatory in time. This is the oscillatory part, and this is the localized part in 3 dimensions. It is just an example to visualize it. Yeah. And from this, one can actually show that all the relativistic and quantum phenomena emerge, and in flat 3-dimensional space, without having to postulate quantum mechanics or introducing Minkowski space. And I will first show this for the relativistic phenomena. All special relativistic phenomena arise as a consequence of this breather-soliton nature of the particles in flat 3-dimensional space, and we do not need to introduce Minkowski space. And the constancy of the speed of light, or time dilation and length contraction, do not need to be postulated. And particles or mass do not have to be introduced a priori. And we can explain the origin of inertial mass and the energy mass equivalence. And also particle mechanics do not need to be made Lorentz covariant, because this directly follows from the Lorentz invariance of the field equations, because the particles are part of the fields. And yes, all relativistic effects occur from motion relative to the rest frame of the field. So the field is something like an ether. It's a field ether, similar to the ether in Lorentz's model. And so also the twin paradox doesn't occur in first place. It is resolved in the same way as it is resolved in Lorentz's theory. Yeah, we first begin with the Lorentz covariance of particle mechanics. Yes, as we said, no notion of particles is introduced a priori. They are part of the fields, namely the soliton. And the energy and momentum of the particle is given by the field energy and momentum. Those are those equations. We saw something similar already earlier. And they formally form a 4-vector, so they transform according to the known laws of 4 vectors when you go into frame moving with minus v. And from this one gets, for a resting breather soliton, that E is some kind of rest energy, E0. You can calculate from the integral above. And P is 0 for a resting soliton. And for the moving one, you get E equals the Lorentz factor times E0, and P is rest energy over c squared times Lorentz factor times velocity. And no notion of inertial mass was introduced a priori, and its place was automatically taken by E over c squared. So this is kind of the definition of the inertial mass, but it comes out naturally. We don't have to introduce this a priori. And yes, combining those equations yields the energy-momentum relation, which is known from special relativity. So the Lorentz covariance of particle mechanics is inherited from the Lorentz invariance of the field equations. Yeah, length contraction. Those elementary particles provide elementary rulers, and their size can be characterized by a certain alpha decay of the alpha is a fraction of 1, for example, 1 over e, of this amplitude function. Mathematically, this is expressed by this. And if one does this for for example, for the soliton here, for this one, but one can also do it for every other soliton obeying a relativistic field equation. Then one finds for the rest length, it is this expression here. And if one considers the same soliton moving, then for the size perpendicular to the direction of motion, one gets the same expression. But for into direction of motion, one gets a contraction by this Lorentz factor. And yes, since all macroscopic rulers are composed of elementary rulers, they inherit this behavior. So the matter is contracted by this Lorentz factor. And it is not space that is contracting, but matter itself. Now for time dilation, the internal oscillation of the particles provide elementary clocks. This was this function here, the oscillatory function. And again, if you evaluate this at rest, you obtain for the frequency of this internal oscillation C over D. D is the 1 over E radius of this particle. And if you do this again for a moving breather, then you get the same slowed by the known Lorentz factor. So the internal oscillations of a moving particle run slower. And again, since all macroscopic clocks are composed of elementary clocks, they inherit this behavior. And it is not time running slower in motion, but just the internal oscillations in the processes of matter. So, and yeah, the constancy of the speed of light, this is the same derivation we already saw in Chantal's presentation. It is exactly the same mathematics. Just one thing to point out, it is not the one-way speed that can be measured directly, but only the two-way speed of light. The one-way depends on a convention of clock synchronization. And so you only have to show that the two-way speed of light is the same in all reference frames. And also the speed of light is only apparently constant, but it obeys the usual normal velocity addition formula, just like any other vector. And in general, the Lorentz transformation are just a pure measurement effect. So you have usual Euclidean space with vector addition, and the Lorentz transformations come out because your rulers and clocks change, and not because space and time is changing. And if you do the calculation and consider that your test section is contracting and your clocks run slower and use the formulas for the back and forth time the light signal takes, then all the effects cancel out and you get the same speed of light C0 in any moving frame. And you can see here from those equations that you have the usual velocity addition. It is just C plus V and C minus V for the one direction, in direction in motion and direction against the motion of the frame. So yeah, the constancy of the speed of light comes out. Yeah?
And in this model, light is going at C with respect to some one frame.
Ether.
Mm-hmm. Yeah.
Well, you're not necessarily saying ether, but yeah,
yes.
I would say the ether.
Yeah, the field ether, yeah.
Yeah, and you would
exactly.
say ether as well.
Yes. Yeah. Okay, this was it for the relativistic phenomena. Now we come to the quantum phenomena.
Just to be clear,
Yeah.
ether is also gravitational field.
Yes.
It's
but I wouldn't.
Magnetic and gravitational.
Yes, I wouldn't necessarily say the gravitation. I mean, I did it with the gravitational field, but I think that it really should only be one field, and that the electromagnetic and the gravitational show up as two different sides of the same field. So it wouldn't make sense to postulate two different fields.
Right.
Yes, and now to the emergence of quantum mechanics. The quantum phenomena are naturally exhibited by solitons, and no quantum mechanics has to be postulated, and we can hope for a purely classical description of quantum mechanics. The wave-particle duality is naturally exhibited by the solitons because they are localized waves with particle properties. So since they are waves, they naturally show effects like diffraction or interference or scattering. And yeah, with the collisions, we saw that two solitons can collide like particles without permanently changing their shape. They retain it after the collision. Yeah, and solitons are spread out wave phenomena, so they naturally obey an uncertainty relation. This is the bandwidth theorem. It is a purely classical theorem, and it is very similar to the Heisenberg uncertainty relation. I'll show in a second. And we can obtain discrete levels for bound states, similar as they arise in standing waves. And it was also shown that solitons exhibit tunneling effects. So a soliton can tunnel through a barrier which a classical particle could not pass. And yes, the de Broglie relations are also included in such oscillating solitons. And from this, a formula for H can be derived. And we will see that this formula coincides in the structure with this coincidence we saw yesterday already.
Do you have a slide on that?
Yes, it will. It will. We will come to this. Yes. Spin can also be explained as just a current flowing in a circular current. Yes, the measurement problem doesn't occur because we don't need a collapse of the wave function. There's no statistical interpretation here. The solitons are real waves. They are not statistical. And yes, and a quantitative agreement with quantum mechanics remains to be shown, that the energy levels in the hydrogen atom are the same from a soliton picture as in usual quantum mechanics. It is not that far developed yet. Yeah, first we begin with the uncertainty relation. As I already said, the wave nature of the solitons naturally gives rise to an uncertainty via the bandwidth theorem. The soliton is a spread out phenomenon, and it is not possible to define a fixed position where the soliton is at because it is spread out around this position. And we can instead define a position as a suitably weighted average, similar to quantum mechanics, as this expression here. This is some kind of a normalization, and this is an average of the quantity g. We multiplied with the phi is the function which describes the soliton or the particle. And then the mean square deviations are just the same as in quantum mechanics. Also, this operator here for the wave number is the same as in quantum mechanics. And these expressions are also the same. And then the bandwidth theorem states that delta k squared times delta x squared is greater or equal to 1/4. This is just a purely mathematical fact. There's no quantum mechanics involved in this. It's just a fact which holds for every wave packet, for every spread out distribution. So it is also not just for nonlinear waves, but also linear wave packets all obey the bandwidth theorem. And the same can also be done with omega and t in the same way as above. And then we get delta omega squared times delta t squared is greater or equal to 1/4. And this is the Heisenberg uncertainty relation apart from the de Broglie relations, which I come to now. So if you plug in the de Broglie relations into those two, then you have Heisenberg's uncertainty relation. So, and how are the de Broglie relations included in the breather solitons? Yes, this was shown by a guy called Enz in, I think, 1985 for the Sine-Gordon model, but it is not specific to the Sine-Gordon model. So what I show here applies to every breather solution of a relativistic field equation. So the only requirement is just that the underlying field equation is a Lorentz invariant. Yes, but I'll show it as an example now for the Sine-Gordon equation. We saw that the oscillatory part is given by that expression here. And from this, we can read of the frequency and the wave number as those here. The frequency is the factor standing here in front of the t, and the wave number is the factor standing in front of the x, and this is those two. But the energy and momentum can also be calculated independently from the field energy, which we saw some slides earlier. And they yield those expressions here. And if you combine those two, then you end up with the de Broglie relations E equals h omega and P equals hk, with Planck's constant given by this expression, rest energy times 1 over e length. The d is 1 over e radius of the soliton over sine q times c. And this has the same structure as the observationally well-established coincidence, which we talked about yesterday, because the rest mass is nothing but the rest energy over c squared. So if you plug this in here, then you see 1c cancels out and you get the same. Sine q is of the order of magnitude 1. And the d was the 1 over e radius of the soliton. And this is the same as the radius of the proton. Yeah. So this suggests that in such a soliton picture, the proton is the fundamental particle. And then you will also have this, this coincidence here. And what is interesting to notice is that those de Broglie relations are a consequence of the Lorentz invariance of the underlying field equations, because the time transforms as this. You can see this from this equation here. For a resting soliton, we only had t on the right side here, but not the beta times x term. And that you get this structure is a result of time transforming as this. If time would only transform as usual Galilean transformation, then you would not get this one here, but you would only have the t on the right side here, and you would not be able to get the second equation for k. So this shows that those de Broglie relations, although they are already present in non-relativistic quantum mechanics, they are really tied to relativity in the soliton picture. And this shows that is a consequence of the common origin of relativity and quantum mechanics in such a Brether-Soliton model. Yeah, how could spin work? What we saw earlier, where did I have it? This solution here with the de Broglie oscillation times the amplitude function. You can also do this with, let me get there. You can also assume that it is not cylindrically symmetric, but that it has some oscillation in phi direction. And then the amplitude function would be in cylindrical coordinates a function of the radial coordinate and the z and the t. And you have a modulation in phi direction. And continuity at phi equals 2 pi requires that this here is actually an integer, as in cylindrical waves. You have this continuity condition at phi equals 2 pi. And you can calculate the energy flux, which corresponds to the field equation we saw. And this is given by this expression. And if you plug in the expression from there into this, then you get a energy current into phi direction. And if you assume that Q over m is constant through the soliton, then you get a charge flowing around in circles. And this leads to a magnetic momentum given by this here. And the magnetic momentum is then pointing in z direction, and it is also quantized because of this. This m here has a discrete value. Yeah.
Do you mean a magnetic angular momentum?
Yeah, I mean a flow. It is you get a current running around. Yes. Yeah. Okay. Yeah, you get a current running around, and this then leads to a magnetic momentum. And yes, this only has discrete values because this ms here has to be discrete because of the continuity condition at phi equals 2 pi. And yes, it can be positive and negative, and it is also discrete multiples of h, as you see in this equation here. And this can, with this you then get the Stern-Gerlach experiment. If the m is positive, then you have the magnetic momentum pointing upwards, and if it is negative, then it is pointing downwards. Of course, one has to explain now how the different discrete values here are distributed to the particles, because some have only 1/2 and one have 1 and one have 3/2 and so on. This one have to explain. It is just more conceptual how one can explain the spin in just this classical way. Yeah.
Don't you also have to explain why the spin somehow always ends up pointing with or against the Stern-Gerlach magnet?
Yeah, this would occur in the same way as Chantal said in her presentation. That it is the same.
The Russian guy.
Rashkovsky.
Yeah.
It would be the same argument, because you basically also have a wave which has which is oscillating in one plane, and it would orientate towards the magnetic field. Yeah, and yes, this current results from a rotation of the energy density inside the soliton with a frequency c over m times d. D is the 1/e radius of the soliton, and c is the speed of light. And this is, so to say, the soliton equivalent to Schrödinger's Zitterbewegung. You also have this, the frequency is c over d. Yeah, and discrete energy levels can also, in principle, occur from when solitons are trapped in a potential well. This is similar to how the discrete modes occur in standing waves. From the boundary conditions, you get the wave number can only take discrete values. And it works in the same way for solitons. And as an example, one can calculate such a sine-Gordon breather we saw earlier, moving in an infinite potential well, and then the boundary conditions at the edges of the well lead to this quantization condition. And if you plug this into P equals hk, the de Broglie relation we derived earlier, and the energy momentum relation, then you get the same energy levels you would also get from the Klein-Gordon equation for the same problem, but with the Planck's constant here derived from the theory. So it is the Planck's constant of the sine-Gordon theory. Yeah, is the soliton model a hidden variable theory? No randomness is invoked to explain quantum phenomena. Those solitons are real waves, like water waves. Rather field waves, but they are real classical objects, and there are no trajectories of point particles hidden behind those waves. So there is not, like in the de Broglie-Bohm theory, you have the wave, and behind the wave there is some point particle trajectory. And this is not the case in the soliton model, but the soliton is the most fundamental reality then. So you don't need to invoke any hidden variables to describe something that is hiding behind the waves. And this is similar to the non-deterministic interpretations of quantum mechanics. And so the soliton model is not a hidden variable theory, and one can expect thus a violation of Bell's inequalities. But a final answer to this has to await an answer to how entanglement works in the soliton model. I don't have any clue for that now. This, I don't know. So, yes, and now an n-particle model, as I already said, integrable field equations or integrable soliton equations have analytic n-soliton solutions, which describe n-solitons and their mutual interactions and the resulting motions in a single solution. And they would then be the quantum relativistic version of the n-particle model like Newton's mechanics or Trader's that we saw earlier. And as an example, I wrote down the n-soliton solution to the Sine-Gordon equation. It is then basically, this V here is the Wronskian determinant, and the C1 to Cn are the n particles. And so you can write this n-soliton solution basically as a determinant of all these single wave functions of the particles. Yeah, then now for the relation to Mach's principle. In the beginning, we got to the soliton model by drawing a conclusion from a unification of gravity and inertia. And so it is to be expected that on the other side, such a soliton model would reduce to something dependent on relative quantities in the non-relativistic limit. And yes, it turns out that this is indeed the case. One can show that when one analyzes the interaction potential between two such Sine-Gordon breather solutions in the classical non-relativistic limit in the lowest order V over C, one gets this form. So the interaction potential is dependent on the relative distances and the relative velocity squared over C squared plus 1. So it has the same functional form as the Machian potentials like Trader's, or also the Weber potential we saw earlier. And it is only dependent on relative quantities. However, if you expand this to higher orders, so if you don't contain yourself to the lowest order, but expand to higher orders, then you also get additional absolute terms, or relative to the absolute rest frame of the field ether. And so this shows or suggests that Mach's principle holds in a non-relativistic classical limit, but that in the general case, you also have a dependence on the velocities relative to the ether, to the absolute rest frame in higher orders when you go to relativistic physics. Yeah, then for conclusion, explaining inertia as of gravitational origin implies that particles are solitons in the gravitational field or a unified field, and the relativistic and quantum phenomena emerge automatically from the breather-soliton structure in flat three-dimensional Euclidean space and in a purely classical framework. Euclidean space is retained with the normal vector addition, and we have no changes in space and time. But instead, it is the matter itself which is changing when undergoing motion. Problems like the twin paradox or the infinite self-energies or the measurement problem don't occur. About the infinite self-energies, I haven't talked, but that they are removed is a direct consequence of particles being spread out distributions and not points, because the infinite self-energies are really an artifact of plugging point particles into the Laplace equation. And if you plug in a spread out distribution, then you get regular self-energy. So this problem is removed. The constancy of the speed of light, the Lorentz transformations, and quantum mechanics, including H, particles and properties like mass or spin need not to be postulated. They arise automatically from the theory. The origin of effects like length contraction and time dilation can be explained. And the universe can be described by a single n-soliton solution that includes the particles, their fields, and the resulting interaction. And this is the quantum relativistic generalization of the n-particle models like Newtonian mechanics or the Machian models. And this suggests instead of unifying relativity and quantum mechanics, both seem to emerge in a different framework from those solitons. And this may provide a gateway to such a unified field theory. Thank you.
I got a question.
Yeah?
Dr. Chang mentioned something that is kind of my intuition has kind of told me that gravity may arise from the strong force.
Mhm.
How does your theory treat hadrons or the strong force particles with the strong force versus electrons? Is it applicable to both, and how are they different?
Well, you can show that such solitons indeed form bound states. So they are held together. If you bring them together under certain conditions, they form a bound state. And this is kind of similar to a hadron, but I won't state that I have anything that I can say now, this definitely is how it works. But you can show that that solitons can form bound states. And also another thing is that I said that the fundamental particle in the soliton picture is the proton, and you can actually show that this thing is constituted of two more elementary solitons which are bound together. And so this hints at something like quarks. I haven't put it in the presentation. Yeah?
Yeah, do you have the formulas for these solitons? Because maybe I can help simulate some of these, unless you have simulations already. But that's something would be nice to visualize, you know, if you have multiple solitons, how they interact.
Yeah, the nice thing is, at least for integrable equations, you have analytic solutions, so you don't even have to simulate them. But of course, the finding for the equations is quite difficult. Yeah. And I think I would appreciate a little numerical help to search for the right equations, because I can only say that they have to be some kind of non-linear relativistic field equation, but I don't have the concrete field equations where I can say, oh, from this I can derive it.
Also visualizations, you know, sometimes
yeah.
to see this.
Yes.
Include me with her.
Yeah.
Help with that too.
Yeah.
Do you see what you've shown us today? How much of it do you see as being compatible with Chantal and Donald's approach, and do you see any contradictions? Any things that can't be compatible?
I think it is in so far comparable that both are in some sense ether theories, and the particles are modeled as something that is moving through an ether, some energy lump that is moving through the ether. And I think the difference is the nonlinearity, that the solitons really are a nonlinear phenomenon and not linear waves, and also not a superposition of linear waves, but it really is and you also need nonlinear field equations. Yeah, Alexander?
Yeah, thank you to begin with. I'm really intrigued by and sympathetic to this approach. So my question might be a little bit asking too much, but you yourself talked about unifying things. So you seem to provide a mechanism for gravity, but you talked also about the magnetic interaction, which differ in strength by a factor of 10 to the 40. They have to be pretty different. Do you have an idea, maybe intuitive one, how to disentangle these two mechanisms? Or if we think about Dirac's ideas, how to put the influence of the universe into one mechanism, supposedly gravity, and how to keep it out and keep it at a local level, supposedly the electromagnetism?
Well, first, I think it should, gravity and electromagnetism really should come out as two different sides of one field, but I cannot prove it. But what is interesting to notice is that one can, if one calculates the interaction between two oscillating solitons, then just as we saw in Chantal's presentation, that whether they attract each other or repulse each other is dependent on the relative phase between them. So this maybe hints at some way how charge could work in this model, but I don't have any concrete idea how it would work. Yeah, Jan?
At some point in your presentation, you jumped from one-dimensional waves to three-dimensional waves, and and then introduced the spin analogy. Can you go back there? I wasn't quite
Yeah.
able to follow along at this point.
Yeah, but it was three-dimensional from the beginning. This here is three-dimensional. It is not one-dimensional. You have an x vector squared here.
All right. So, yeah, all right. So,
But I just for the sake of simplicity, I just showed the stuff here in one dimension, because this was the work. It was originally done by Enz with this one-dimensional Sine-Gordon model.
so then, do you have a three-dimensional nonlinear differential equation to which you have found Soliton solutions which exhibit the spin phenomenon?
Well, first for this derivation here, it works exactly the same in three dimensions. I just showed it in one dimension for the sake of simplicity.
Yeah, all right. Can you show the spin
Yeah, sure.
stuff again?
Yes. Yeah. This is a three-dimensional. You have the.
All right, but this is a general case. It's not a specific Soliton solution to a three-dimensional.
Yes, but you can do it with this one I had over here. You can modify this solution here. If you solve with this potential, you can do it in cylindrical coordinates, and then you get just this term here. Then is not rho squared plus z squared, but it is z squared plus some function of rho. But otherwise, the structure is the same, just with the I m phi standing in front of here.
Right.
Yeah, Jonathan?
Can I ask a question that's also related to Chantal's talk? Is how do we deal with Bell's theorem, this kind of classical interpretation of quantum mechanics?
Yeah, as I said already, a final answer has to await how entanglement works to resolve it. But as I said, it is suggested that Bell's theorem is violated because it is not a hidden variable model. So you don't have any discrete trajectories hiding behind the waves, but they have more similarities with the non-deterministic interpretations of quantum mechanics, because the wave function really is the most fundamental reality. You do not have anything hiding behind it.
You're saying they have more similarity with non-deterministic?
Yeah, from the formalism, yes, but not with the interpretation.
Because we could still interpret, I don't agree with the difference between theory and interpretation, but like on this deeper level, you could still, you could say that if it, that there is a hidden variable, and that is whatever it is that causes the wave to collapse at any particular point, and that is the hidden variable. But you're saying what's given so far, what you've shown us, doesn't have a hidden variable. It treats that collapse as truly random.
No, you don't even need a hidden variable. It is just the wave itself, which is
Then
all
how
there
do
is.
you account for the randomness of a detection event? The apparent randomness of a detection.
Well, I showed how you can derive the uncertainty relation from the Soliton model. So the uncertainty relation is basically this. It is just a bandwidth
The
theorem.
uncertainty relation, that's the thing. People sort of mix this up with the other paradoxical results in quantum mechanics, but uncertainty relation is really just a consequence of wave.
Yeah.
Okay, so you have
Yeah.
the same thing with the Gabel limit in time series analysis. So it's, but yeah, in any case.
Hey, I see this as a hidden variable theory when it explains also the entanglement. And there is your nonlinear equation we discussed, also admits solitons of the form, and there is a little phi. I have a capital phi, and it's from global origin, and it is like a hidden variable, so that entanglement can be explained.
Okay.
I would say that entanglement is a false philosophical concept. and one has to actually look at what the experiment was and how it progressed,
Mhm.
and then you can find an actual physical explanation for it. And they just really, it's because quantum mechanics has only looked at, observers' information.
Yeah.
They have two comments. So Robert Close, who I mentioned in my talk, he has actually done a lot of work also on solitons. I didn't mention it because I only had 1 hour, but actually he also talks about this. So I don't know, maybe you and him could connect or something, because I think there's a lot of content that overlaps.
Sure. Yeah, I
so
would.
Maybe both combined could lead to something new. And the other thing is I have done some simulations on the Bell type experiments using classical waves,
Mhm.
and you can easily get the CHSH result. You can kind of break it if you use classical waves, just simply based on the way how light is detected. Based
Okay.
On the so anyway, I mean, this is for another conference,
but both very interesting. Yeah.
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 Do any leads spring to your mind on how one could make inferences proving any of this?
Well, if first of all one would have to find the correct soliton equations. This I don't have them now. It was more an overview of how the things would work, but the correct soliton equations remain to be found. But one is on the one side, you can explain many things that are postulated currently. And another one is this currently coincidence of the Planck's constant. This would then be a prediction of the soliton model. So, and since this is, it is measured, and it is the same as with the formulas of G we saw in the Machian theories. This is a prediction of the theory, because currently it is not explained, it is just a coincidence. And those models predict this. And it's the same in the soliton model with the equation for H.
Any last questions? All right.